Hello, everyone. In this video, we want to talk about what a saturated solution is and how to find the solubility of it. So to do so, we have to introduce what saturated solution means. So a saturated solution is a solution in which maximum amount of solid is dissolved and there's no more room for dissolving any more solid. So if you add any more solid to it, it will start making it precipitate. And then solubility is a measure of that maximum. So it's the maximum amount of solid that you can dissolve in certain liter, certain volume of water without it forming a precipitate. So basically, in order to make a saturated solution. So solubility can be found in two units. Either you can find it in grams per liter or you can find it in moles per liter. If you find it in moles per liter, it's also called molar solubility. And then for my calculations here, I'm going to be using the symbol S for solubility. Some textbooks or some teachers might use X for finding solubility. For me, I think it's better to use S just because the letters match and hopefully it will remind you that you're actually trying to solve for solubility. So let's now look at some equations for solubility or a saturated solution. So any saturated solution that it's given to us, we have to know how to write this balanced equation for it, for that saturated solution. So to do so, we have to always have the solid on the left, the ions on the right, and then we have to have the equilibrium symbol in between. So for example, in the case of AgCl, the solid is on the left, Ag plus ion and Cl minus ions are on the right, and then we have the solubility equilibrium in between. For PbBr2 is the next example, same thing. The solid on the left, the ions are on the right, but we have to watch it that in this case, in the case of PbBr2, we end up getting 2 Br minuses, and that's because of the subscript underneath it, which indicates that there is 2 Br minuses in that solution. And then we write the equilibrium in between, and that's how we write the saturated solution equation, basically. Just in case if you don't know how to find out how many of these ions you have, I have another video that I'm explaining in it how to figure out how many ions are in an ionic compound. So in case if you want to, I can tag it over here and you can watch it. Okay, so for the next example, copper 2 phosphate. So we end up having the solid on the left, the ions on the right. So we end up getting 3 copper 2 pluses on the right, and then 2 phosphate ions on the right as well. So this is how we write the equation. Now, next thing is if they ask us to find molar solubility of a saturated solution. So molar solubility is the thing I showed with the symbol S in my calculation. So to do so, first thing is we have to write the saturated equation for all of them. And then second is whatever the solubility of AgCl is, for example, for Ag plus and Cl minus would end up becoming exactly the same. So it has to do with the stoichiometry, with the coefficients in this balanced equation. So for example, for lead-2 bromide, whatever the solubility is, the concentration of lead-2 plus in that solution and the concentration, it would be S, and the concentration of Br minus in that solution would be twice as more, so 2 times S. So for copper 2 phosphate, the solubility is S. So the concentration of copper 2 plus would be 3 times that, and the concentration of phosphate ion in that solution would be 2 times that. Now, to find molar solubility, we have to introduce another constant, which is called Ksp, or we call it Solubility Product Constant. So Ksp is technically same as K equilibrium. So if you remember from the equilibrium unit, Ksp or K equilibrium is the concentration of products over concentration of reactants. So same, but this time when we say Ksp, we're exactly referring to a saturated solution. So to find Ksp, we have to do the same thing over here. We have to write the concentration of products over reactants. So it would be concentration of Ag plus times Cl minus, but we want to say over AgCl. However, the thing is AgCl is a solid, so it doesn't have a concentration. So basically Ksp equations are always just about the product side, and the reactant side is not going to be written for them. So therefore, if I substitute these concentrations by the S or their concentrations, it's going to end up being S squared. So Ksp would be S squared. For the next one, PbBr2, Ksp would be concentration of lead-2 plus times Br minus squared. So if you remember again from K equilibrium, anytime you have a coefficient, the coefficients would become exponents when you're writing the Ksp or K equilibrium expression. So same thing happens over here. So because of the 2 next to the Br minus, it will now become to the power of 2. And now next step for us is to substitute it with the S symbol. So it's going to be S times the 2S, and now the whole 2S has to be squared. So it's going to end up becoming 4S cubed. So Ksp is now 4S cubed. For the next one, the Ksp expression would be concentration of copper 2 plus to the power of 3, concentration of phosphate ion to the power of 2, and then we're plugging it in with 3s and 2s. So 3s this time has to be cubed because of the coefficient of 3 next to copper 2 plus, and 2s has to be squared because of the same reasoning, and we end up getting Ksp to be 108 s to the power of 5. Okay, so here we have a Ksp table. So this is a table that has some ionic compounds in it with our Ksp numbers at 25 degrees. First of all, it's very important for each table to mention the temperature because Ksp is K equilibrium basically, and K equilibrium is temperature dependent. So depending on the temperature, the value will change. That's why they have to mention the temperature. Second thing is I want you to note that all these values are basically less than 1. If you look at them, they all are 10 to the power of negative 9, 10, or whatever. So that means when you have a saturated solution, even though it's an equilibrium going on there, however, the left-hand side or formation of the precipitate or the solid is more favored than the formation of the ions, basically than dissociation, than dissolving. So if you think about the forward direction as dissolving and the reverse direction as precipitation, precipitation is always favored for these ionic compounds because they have such a low Ksp value and they want to be more in the precipitate form than in a dissolved form. So usually when you see solutions like anything like the ones that are listed over here, they right away form a precipitate. They're not one of those things that really want to be dissolved. They'd rather be in the solid form. All right, now let's do some questions that involve calculations for Ksps and solubility. So let's say the first question is asking, find solubility of AgCl at 25 degrees. So to do so, first step for us is to write a saturated equation and then put the solubilities and concentration of ions in that saturated solution based on the symbol S. Now, next step is to write the Ksp expression, and then we substitute it with the symbols S. So Ksp would end up becoming S squared in this case. So all I have to do over here is to grab the Ksp number from this table, which is 1.8 times 10 to the negative 10 for AgCl, and therefore it's going to be equal to S squared. So to find S, we have to get the square root of that, and solubility or molar solubility will end up becoming 1.3 times 10 to the negative 5 moles per liter. So see here, it's not asking for molar solubility, but because they didn't mention the grams per liter, you have to always assume it's for moles per liter. So you have to find it based on moles per liter or molar solubility. All right, let's take a look at another question. So this time it's asking to find the solubility of PbBr2 at 25 degrees. So same steps. First is to write the saturated equation. And then second is to substitute the S's and concentrations and solubilities based on the coefficients. Then write the Ksp expression. So this way it's Pb2 plus times Br minus to the power of 2. So it's going to be Ksp will end up becoming 4s cubed. Now we just grab again the Ksp from the table, which is 6.6 times 10 to the negative 6, and that's equal to 4s cubed. So to find s, we have to divide the Ksp by 4 and then get the cube root of that, which end up being 0.012 moles per liter. Now, imagine they give us another question and they say find the solubility, but this time they say find it in grams per liter. So they're not asking for molar solubility. They're not asking for moles per liter. So all the steps would exactly be the same. We just have one extra step right now. So we know the solubility in moles per liter. So using the molar mass, we have to convert that to grams per liter. So we know for every 1 mole of PbBr2, the molar mass is 367 by adding up all the masses in the table. This way moles cancel out and we end up getting the solubility in grams per liter, which is 4.4 grams per liter. Now let's take a look at another example. It says find solubility of copper 2 phosphate at 25 degrees. So same thing. First step is to write the solubility equilibrium. Second is to write the concentrations and solubilities based on their coefficients. So S, 3S, 2S. Then the Ksp expression. And then we plug in the concentrations based on their 3s and 2s basically. So it will end up being, Ksp ends up being 108 s to the power of 5. So my table doesn't have the Ksp value for this compound, so I had to search it. But if your textbook has it, you can grab it from there. I searched it, and the Ksp was 1.4 times 10 to the negative 37. So that equals to 108 s to the power of 5. So to solve for s, or solubility, we have to divide the Ksp value by 108 and then take the fifth root of that, and the answer will end up becoming 1.7 times 10 to the negative 8 moles per second. Okay, so thanks for watching. If you find this video helpful, please like it and subscribe for more. Your support means a lot to me. See you in the next video. Bye.